we're all here today. We're super excited that Bezalem is going to be sharing her work with us on multi-level Bayesian networks for hierarchical data. She is currently finalising her PhD in statistics, where her research is focusing on multi-level Bayesian networks. Her work has been recognised through a series of awards, so the L'Oreal UNESCO for Women in Science, Sub-Saharan African Award, Schlumberger Foundation Faculty for Future Fellowship, and travel support from the International Biometric Society, so a bit of a superstar. She's also been a member of BNMA since 2023 and received a travel grant to attend the conference in 2026, although sadly wasn't able to join us in person, but she still got the award, so that was good. Prior to her PhD, she's worked as a lecturer and a researcher at 3 different universities in Ethiopia, where this is where she developed her academic foundation interest in statistical modelling. So we're really excited now to let Beza tell us a bit about her PhD work. Over to you, Beza.
Thank you, Helen, for the nice introduction. Hello, everyone. Today, I will be sharing part of my PhD work that focuses on multilevel Bayesian network, which extends standard Bayesian network to handle hierarchical and correlated data, such as multilevel data and longitudinal data. I will begin by motivating why such extension is needed. So let me share my screen first. Do you see my screen?
Perfect.
Okay. Okay then, so why we need such an extension in Bayesian network? Because in many real-world applications, especially in public health research, data are not independent. For example, most of the time, patients are measured repeatedly over time, and they are also grouped within hospitals or regions. Similarly, for example, to study the effectiveness of some nutritional supplements in some area among children, children can be grouped in village or some geographical area. So in this case, we believe that the individuals from the same group or from the same clusters are correlated due to some shared factors. This creates 2 sources of variations, which is a within individual variation and the between group variation. So, and this must be properly accounted for to avoid the biased results, because ignoring these dependencies will lead us to the biased result in Bayesian network, biased structural learning, and biased parameter learning. Okay. So what are the existing approaches to handle such types of data, multi-level or longitudinal data? Most of the time, we use multi-level or mixed effect models. They are widely used to handle hierarchical and longitudinal data. They account for the within and the between group variability. However, they typically focus on a single outcome variable, and we have to specify the outcome variables and the predictor variables in advance before starting fitting the model. So that is a limitation of multi-level or mixed effect models. But what if we want, what if it is important to model the dependency or the conditional dependencies between multiple outcome variables? For example, as you can see from this graph, it shows the conditional dependencies between multiple outcome variables, health conditions like diarrhea, pneumonia, weight for height, dehydration, and and dehydration and acute gastroenteritis. So if we need such types of dependencies to model such types of dependencies, as well as to handle the within and the between group variability, we need a framework that can handle both the conditional dependencies between multiple outcome variables and as well as handle the hierarchical structure of the data. There are some related works from previously. Some studies explored combining Bayesian network with mixed effect models, but has their own limitations. For example, the work from 2013 does not consider the inclusion of random effects due to the higher level clustering variables during the structured learning. And in Bayesian network, structured learning is the first step and it's the basic step. If we miss the structure, we miss the parameters and everything. Okay, so now let me formally introduce what multilevel Bayesian network is mathematically. So a multilevel Bayesian network, it's an extension of standard Bayesian network, and it incorporates the hierarchical structure of the data. Formally, it consists of a direct acyclic graph, a set of random variables, a clustering variable, and along with the joint probability distribution. So everything is the same with Bayesian network, but the key difference is on the likelihood, So the key difference between the multi-level Bayesian network and standard Bayesian network is each local networks include random effects in multi-level Bayesian network to capture the influence of higher-level clustering variables. That means, in other words, the likelihood of the network is updated to include the random effects, allowing us to properly account for the within cluster correlation, and while learning the network structure and learning the parameters also. So this is a likelihood. So we add here L. L is to indicate the higher level clustering variable. It can be hospitals, for example, if we are studying grouped patients at different hospitals. L can be the hospitals. If for longitudinal data, L can be individual ID. And theta yj is here the notation. Let me introduce the notation here. Yj is the J's outcome variable or the J's variable or the J's node. Ydj here is the parents of yj, and L is the clustering variable, and theta yj is the parameter space for the J's outcome variable. Okay. In a multi-level Bayesian network, each local network is modeled using mixed effect models. Using the mixed effect models here, Yij is L's individuals, the I is individual in the L's cluster. I separated this into multi-level data and longitudinal data. But I made this just to make it simple. Not this is a general formula for mixed effect models. But in case there are someone who are not familiar with mixed effect models, I just separated them. But this one is the general formula for the mixed effect models. So the likelihood for each of the local network can be modeled using the mixed effect models like this. And Zj are the covariates or the parents of Yj, the parents of Yj, which are associated with random effects. And here Ydj is, or this one in matrix 4, Ydj is the covariates or the parents of Yj associated with the fixed effects or the fixed components of the model. That is, we have two components in mixed effect model, the random and the fixed part. So these are the fixed part, and most of the time in multi-level Bayesian network, the random effects and the fixed effects, we take the same variables. So here Uj, the random effect, is normally distributed with mean zero and variance covariance matrix. And we have Ej is a error term, which is also normally distributed with mean zero and the variance parameter. But here we start the multi-level Bayesian network by first only including random intercept to check we just only include random intercept first. That means we omit the Z part and only UJ. That means in this case, we only have one variance parameter here. We don't have variance covariance matrix. It will be one variance parameter. And then we introduce a random slope and a correlated random intercept and random slope in the case of longitudinal data, because in longitudinal data, it is most of the time it's common to include the random intercept and random slope, and sometimes correlated random correlation between random slope and random intercept. So in this case, we have at the fixed effect at the fixed component of the local network model, we have TILG. Here is the time points, and we also have the time points at the random effect part. And generally, we have a vector of random effects for the random intercept and for the random slope, which has a normal distributed with mean 0, vector of zeros, and variance covariance matrix. So this variance covariance matrix can be decided by looking at the data set using some exploratory data analysis. So the full variance covariance matrix for the random effects of the P nodes in the multilevel Bayesian network is a diagonal variance covariance matrix, and each diagonal elements are they are themselves variance covariance matrix for each nodes. And here, structured learning. Structured learning is the first step in learning Bayesian network, and we have two steps in structured learning. That is the score function and two components: the score function and the search algorithm. For this talk, I will be just focusing PIC score and the hill climbing search algorithm just for simplicity. But for my work, I also use a connected 3-parent set block keep sampler, which is I've done it in MATLAB, and also the marginal likelihood score, which is the Bayesian score function. And for the parameter learning, I will be focusing using the maximum likelihood estimation method for this talk. So why multilevel Bayesian network? Why multilevel Bayesian network? So because multilevel Bayesian networks are designed to handle hierarchical and longitudinal data, they capture both the within and the between subject variability in terms of longitudinal data, and in terms of multilevel data, they can capture both the within and the between, the within individual and the between cluster variability. So, but what happens if we apply standard Bayesian network to such types of data for longitudinal data and for multilevel data? So in this case, the independent assumptions of Bayesian network is violated, so which leads to the Bayes structured learning and Bayes parameter learning. So here I present a small part of the simulation study, which shows the effect of ignoring the hierarchical structure of the data and applying Bayesian network for longitudinal data set, where I simulated the longitudinal data with 200 individuals and 8 repeated measurements. Since I'm using the BIC score since we are using the BIC score and the maximum likelihood estimation method, we need a large sample data. So for this one, so I used 200 individuals and 8 repeated measurements. And the data are generated from a non-directed acyclic graph with 6 variables. Because our focus is to compare these to the multilevel Bayesian network and Bayesian network, the standard Bayesian network, and to introduce the dependency, to introduce the hierarchical dependency, we include the subject level random intercept and random slope, and we allowed them to be correlated, and we used ICC between 0.2 and 0.4. I think I've seen some message here. Sorry.
That's fine, Bezo. We're just talking about the recording. All good.
Okay. I'm sorry. Okay. So here I use a structure Hamming distance and area under the receiving operator characteristics and F1 score to compare the structure learning. I only present the structure learning, the simulation study for the structure learning part to save time. So the structure Hamming distance measure how the learner network is how far the learner network is from the true structure, and we see that multilevel Bayesian network achieve near zero SHD, as you can see here, near zero SHD, and indicating almost perfect recovery, while the standard Bayesian network here has high SHD. So which tells us that using standard Bayesian network for multi-level data or longitudinal data, that means ignoring the hierarchical structure of the data, leads to the biased structure, and this the result from the AUCROC and F1 score also supports the same results here. For AUCROC is almost 100% for multi-level Bayesian network, and for Bayesian network it's a little above 50, 0.5, and F1 score also shows us the same result. And illustrative examples, I just here present child morbidity data from which is collected from primary health clinics in Addis Ababa, Ethiopia, to illustrate the application of multi-level Bayesian network. A total of 120 children, each with at least 5 follow-up measurements were included in the analysis. Although the intended time interval was 1 week, but in practice, the data exhibit irregular measurement times. The time interval between the first and the second, they are irregular, and that's the limitation. So here, since it is a longitudinal data, it's this figure shows the individual profile plot, also known as which is a spaghetti plot, for one outcome variable, which is weight for height. And exploring such plot is very important to understand the data structure and to guide the specification of the variance covariance matrix in the variance covariance components in the model. So as we can see here, children have different weight for height at baseline, and they have different slopes, which means which shows us the importance of including random intercept and random slope. And as we can see here, in addition, it shows a small fanning structure, so a fanning pattern here, which shows maybe it is important to include the correlation between random intercept and random slope. And here, this is a learned structure, the directed acyclic graph, which is learned using the multilevel Bayesian network using hill climbing approach. So this one is RUTF is a ready-to-use therapeutic food, which was provided to improve their nutritional status. So the model, as you can see, the model capture multiple comorbidities like diarrhea, weight for height, which is weight for height, one of indication of malnutrition, pneumonia, acute gastroenteritis, and dehydration. So in the model captures these multiple comorbidities, and it shows a plausible structure clinically, except for one age from diarrhea to age, and this is due to the small data set, and because I use only 120, I just present this example as an example, but I use this one to compare the effectiveness of the score function, the Bayesian score function in the likelihood score function. So this is how multilevel Bayesian network work. This is all about the theory shortly in multilevel Bayesian network. Now I will stop this sharing this screen and share my R records and say a little bit how it works. If you have any question before I start the practical session, you can throw.
Any questions, just maybe raise your hand or pop them in the chat, and we'll keep an eye on that.
Do you see my?
Yep, we can see the code. We can see your R code, yes.
Yes, okay, thank you. Okay, now I will move to the short practical session here. The R session, which can be implemented in practice. Most of my implementation was done in MATLAB, as I told you before, using the connected three-parent set block give sampler to learn the structure. But for this demonstration, I will be using the build-learn package in R, as it provides a very simpler framework for illustrating the key ideas in such a short time. So if anyone is interested in the MATLAB implementation, I will be happy to share further details with you. Okay, first I will show the multi-level Bayesian network only with the random intercept. The random intercept. Now we here we cannot use we are not going to use built-in score functions in the bin-learn package because we are using our own score function. So here I have a score function here. It is for the random intercept, and one here indicate only it indicates we only consider random intercept. So we use LME package. LME are a function from the LME4 package. So this is the score function. And this setup, so we use LME our function from the LME4 package to fit the mixed effect models, and then compute the BIC score based on that model. Here, finally, we recover the BIC score. I put minus here because in hill climbing, BIC score from the mixed effect models is a better model is the one with the smallest BIC score. But in the build-learn package, the hill climbing algorithm knows that the better model is the one with the highest one. So to make it convenient with that one, so I just put minus here, and part of this code is adapted from previous literature. And now and we specify the grouping variable here. The grouping variable, we have the grouping variable, and structure. To learn the structure, we have to specify the grouping variable here. Our grouping variable is G. Let me show you the data. This is the data. The data set, it is I simulated 30 clusters, each with 50 individuals. So we have 30 clusters here. This is the third cluster, the fourth cluster, and so on and so on. I only consider here the Gaussian outcome. I will show you also the one with the Gaussian in binary outcome. So we specify the grouping variable as you see from the data set. The grouping variable is G. So here we have the data set, data1. So we use a custom score function, and we call our score me function, which we write it here. And then finally run, we can run and get the values, our structure. Let me show you that one.
So we've got 5 minutes left.
Oh, really? Okay.
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 We can stretch to 7, I think.
Yeah. Okay. For the hill climbing approach, I recommend random restart. I didn't put it here because it takes a little time. Not only 2, 20, 50. For real data application, I recommend using as much as possible random restart. To plot, we already learned the directed acyclic graph here. We have already learned the structure. This is our structure. The details about the structures we have. So we whitelist all the edges from the grouping variable to the nodes, to all of the other nodes, and we blacklist all the arcs from the other nodes to the grouping variable. If you want to plot the DAG, it looks like this. I just make the green color here to show that we consider random effects due to the higher level clustering variable G. For parameter learning, here the parameter learning, we also use a lemme for a function and the fit-me1 function, which we use to learn the structure. And what this function do is just it extracts the fixed effects, random effects, and it calculates the variance that is the variance for the random effects, and then give us the results here. So it looks like this. For example, here for Y7, we have 2 fixed effects, and this is the intercept, and we have the variance components. We can make the parameter learning we can make it 2-step if we need further analysis using this function. I don't have time to explain everything, so let me just show you the parameters, the learned parameters here. See, for example, here for this is for Y10, it have 4 parents, and we have G as a random effects. So as you can see, they have different, each of the cluster have different values, but the fixed effects are similar, the same, because we didn't allow the other parents to have random values. So this is for, this application is very good, especially after, for example, after fitting or after learning the parameter using the first step. If we see high variability or high variance for some node, we can investigate by pinning down to that node, just like this. And then we can identify the clusters with the higher variance, with the higher value, and we can investigate why this cluster have high values. So random intercept plus random slope, this is for longitudinal data. I have the data set for the longitudinal data. This is the data, and this is the data. I simulated 200 individuals, each with 8 repeated measurements. 8 repeated measurements. So first we have to do some exploratory analysis, like ggplot, spaghetti plot. As you can see from this spaghetti plot, they have different intercept and different slope, and it have some fanning structure pattern for all of the nodes, indicating that the importance of including random intercept plus random slope plus correlated random intercept plus random slope. So we have this score function again. The difference from this one is the extension of the first one. That one only include random intercept, but we have random slope due to with respect to time here, the time points. So I will just show you the results. Structure, I'm learning the structure. We have to specify the time T and the ID, the individual ID, and whitelist, and we have to put our blacklist just like the previous one. So this is it might take a little time, just 1 minute. And similarly for parameter learning, we have our directed the structure. We have already learned the structure, and this is the structure. And to learn the parameter, we use the same score function. We use the same function from the score function to compute the score during the structure learning. This one, and we can learn the parameters. But here, this parameter learning too, what does it do is it extracts the fixed effects, the estimates of the fixed effects and the variance covariance matrix. This LME package give us a correlation, so we extract the correlation, the variances for the random effects, and then here it calculates the covariance and finally give us the variance covariance matrix plus the fixed effect parameters. So this is how it looks like. Now the difference is we have here this is the fixed effect part, and this one is a random effect part. We have these estimates for the fixed effects. They are constant across individuals, but here we have the time, the variance due to time with respect to time is 0.5. The variance, the subject level random intercept variance is 0.6. And we have a covariance between the random intercept and random slope, so we can learn the parameters just like this. And we can also further investigate the parameters using the same function here, but a little extension. We add T, the time points. Since we don't have time, I'm not going to show this. Maybe I will share the code. And for hybrid MBN, means I consider here the Gaussian outcome and binary outcomes. Here the difference is if it is binary, I just put an if condition. If it is binary, use the JLMER function, and if it is not binary, use the LMER function, from the LME4 package, and it can learn. So we have to factor all the categorical variables. And we have whitelist arcs, we have also blacklist arcs, and we learn the structure just like this. And
We've got
we do okay, I already finished, sorry.
Oh, no, so I was just going to say, we've got a question in the chat for you, Beza.
Okay. Bayesian hierarchical models can be set up to do. Yes, for the first question, yes, I do the Bayesian hierarchical. Yes, I use a Bayesian hierarchical modeling, but for especially when we have small data set. I combined this structured learning with INLA and use the marginal likelihood function from calculate the marginal likelihood score using INLA, the integrated Laplace approximation, using the RINLA package. So in that case, I combine the structured learning with the RINLA package. So yeah, it perfectly learns. If we have a large data, the performance is the same with this one. If we have small data, the using Bayesian hierarchical modeling is better. If it were possible, it would be great to be yes, I can share the code for the second question. If it is possible, it would be great to get an R or B learn example for illustrative case that you mentioned, children in health clinics in Ethiopia. Yes, I can share that one, but I cannot share the data because of the ethical approval. So you have to communicate with the Addis Ababa Health Bureau to get the data first. But I can share the code. Any other question? Since we have considering categorical variable here, it takes a little time than the Gaussian outcomes, so it takes a little time. And especially if we add a random restart, it takes time. Any other question till we get the results for this one? We can discuss.
I was just going to ask, was there any surprising or unexpected results? Like you obviously had a kind of hypothesis for which scenarios it would work better in. Were there any results you got in your thesis that you weren't expecting or that worked better than you thought they would?
I couldn't get your question very well. Can you explain?
Sorry, I was just saying, were there any results in your thesis that you didn't expect? Like, did you have any models that worked better than you thought they would?
Yes, especially in the INLA case. I proposed the last project was we proposed the INLA MBN, which combine the integratedness Laplace approximation with a Bayesian network. That one gave me a very surprising result. It's very good actually. It performs very good. It perfectly learns, especially for small data set. Most of the time when there are outbreaks or something, we might be challenged to have a very small data, small individuals, and the repeated measurements maybe 5 or something. In that case, this one have a very problematic, but that the INLA using some prior, but we have to include the priors. And there is some built-in priors in the INLA package. Most of the time people use them just as it is. But those priors are doing better for large data set. But if it is a small data set, we have to do some sensitivity analysis to include the better prior.
Excellent, thank you. Are there any further questions?
So the result is here we have yes, we have the result. We already get the structure. So based on the structure and the data set we have, we can learn the parameters. So these are the parameters. We have unstructured variance covariance matrix for each of the nodes. We have the intercept, the intercept. We have also random, the variance for the random slope. And we have, sorry, this one is a correlation. The correlation, I just mistakenly said covariance correlation. So this is a fixed effects. And the fixed effects are similar across the group or across individuals. We also did for different fixed effects, for different we also added in the next extension we did multi-level Bayesian network with more than 2 correlated random effects. That means adding some of the parents as random. So in that case we have a k times k plus 1 over 2 parameters in our variance covariance matrix for each node. So this is how we learn the structure and the parameters. The time is not sufficient, so I might share the code. Yeah.
Excellent. Thank you so much.
Uh,
That was, sorry, I can just commend your bravery in showing your code. I would never let anyone see the code I write because it's a disaster. But your code is just so beautifully elegant.
Thank you.
Were there any further
yeah.
questions? Oh, sorry, go ahead.
Just let me share my other screen and sorry if I have time. Share my email address in case someone want to contact me.
Ah, perfect. Thank you. Yeah.
These are my acknowledgements. I really and these are my email address. This is my institution email address. But this one after 1 year, I think I might not be available with this one, so you can take this one, the Gmail address.
Excellent. Well, thank you very much, Bess. That was really interesting, like just seeing what you've been up to. And I know that hierarchical modeling and dynamic modeling is something we all sort of struggle with Bayesian networks. So it was really good to sort of see what's happening in that space and see someone actually tackling the problem. So thank you very much, and
Thank you.
congratulations on the submission of your thesis.
Thank you very
we
much.
look forward to seeing more amazing things that you get up to. And
Yeah.
thank you everyone very much for joining, and please do join us for the next webinar, which will be announced on the